What if I told you that some of the most precise predictions about our universe didn't come from supercomputers or billion-dollar telescopes, but from patient observers in the 1800s, armed with little more than a notebook and a simple lens? Picture this: under flickering gaslight, a lone astronomer squints through a brass telescope, tracking the slow dance of a comet across the night sky. Night after night, they jot down its position, noticing subtle patterns invisible to the casual eye. Decades later, their handwritten notes reveal a trajectory so accurate it rivals modern calculations. How is it possible that these skywatchers, working with tools we'd now consider primitive, could foresee celestial events that even our most advanced technology sometimes misses? This isn't just a quirk of history, it's a testament to the power of human curiosity and relentless observation. Long before algorithms processed data or satellites mapped the heavens, these dedicated individuals decoded the cosmos through sheer patience and precision. They predicted comet flybys, solar flares, and even the behavior of distant stars with an accuracy that still baffles scientists today. Some of their discoveries were so ahead of their time that we're only now uncovering the genius behind their methods. What did they see that we've overlooked, and what can their forgotten techniques teach us about the universe today? That's the mystery we're unraveling in this video. We'll travel back to an era when astronomy was as much an art as a science, piecing together clues from weathered journals and long-forgotten observations. Along the way, we'll discover how these skywatchers turned the night sky into a living map, one that held secrets modern technology is just beginning to rediscover. From comet chasers who rivaled supercomputers to the surprising ways their work still shapes astronomy, this is a journey into the past that just might change how we see the future of space exploration. So let's step into the shoes of those 19th century observers and uncover the hidden wisdom written in the stars. Imagine watching the same patch of sky every night for 30 years, tracing the faintest glimmers of light with nothing but your eyes and a notebook. That's exactly what astronomers like William Herschel did, transforming patience into a superpower. While today's telescopes capture terabytes of data in seconds, Herschel spent decades sketching the same star clusters by hand, noticing subtle shifts in brightness or position that even our most sensitive sensors might overlook. His meticulous records of Uranus's orbit, for example, revealed gravitational tugs from unseen planets, clues that would take modern astronomers another century to fully understand. This wasn't just about persistence, it was a different way of seeing. Where modern instruments scan the sky in snapshots, 19th century observers lived with the stars, watching them change over lifetimes. Take variable stars, those that brighten and dim in cycles spanning years. Automated surveys today might flag them as anomalies, but astronomers like Henrietta Swan Leavitt tracked their rhythms like clockwork, discovering patterns that became the foundation for measuring cosmic distances. Her handwritten notebooks filled with carefully plotted dots unlocked a secret language of the universe that flashy tech could easily miss. And then there's the art of planetary atmospheres. Modern probes might analyze Jupiter's storms in high resolution, but it was observers like Giovanni Cassini who first noticed the great red spots slow drift across centuries, a detail lost in the noise of short-term data. These skywatchers didn't just record what they saw, they absorbed the sky's cadence, spotting changes too gradual for algorithms trained on speed. So what happens when we combine their patience with today's tools? Projects like the American Association of Variable Star Observers now blend historical records with AI, proving that the old ways still have value. Maybe the next cosmic breakthrough won't come from a faster telescope, but from someone willing to sit with the stars, just as Herschel did, letting the universe reveal itself one slow, deliberate observation at a time. Think about the last time you tried to sketch something from memory, the way your hand instinctively emphasizes certain details while glossing over others. That's exactly how 19th-century astronomers mapped the cosmos, turning their careful observations into hand-drawn celestial masterpieces. Unlike today's digital images, which often flatten subtle variations into uniform pixels, these sketches preserved anomalies that cameras missed entirely. A faint smudge in a nebula, the slightest dimming of a star, these were recorded with an artist's precision, revealing patterns too delicate for early photographic plates to capture. When William Parsons sketched the Whirlpool Galaxy in the 1840s, his drawings showed intricate spiral arms that blurry photographs wouldn't resolve for decades. There's something almost poetic about how these observers documented transient events. Take solar prominences, those fiery arcs leaping from the sun's surface. Early cameras, with their long exposure times, smeared them into indistinct blobs, but artists like Etienne Leopold Trouvelot rendered them in stunning detail, their sketches hinting at the plasma's motion and structure. Those delicate lines weren't just art, they were data. Trouvelot's work, for instance, revealed solar dynamics that physicists later confirmed with spectroscopes. Then there's Caroline Herschel, whose notebooks overflowed with observations modern software might dismiss as noise. She logged faint stars and nebulae with a consistency that bordered on obsession, and her records later helped identify variable stars and deep sky objects. Today's algorithms, trained to filter out irrelevant fluctuations, could easily overlook these subtle clues, but Herschel's handwritten notes preserved them, each entry a potential key to cosmic mysteries. So what happens when we marry these old-school techniques with cutting-edge tech? Projects like the Zooniverse platform now invite volunteers to analyze digitized historical sketches alongside telescope data, uncovering anomalies that neither method would catch alone. Maybe the next big discovery won't come from AI scanning petabytes of space images, but from a researcher flipping through a 200-year-old sketchbook, spotting a detail everyone else overlooked. After all, the universe speaks in whispers, and sometimes you need a human hand to translate them. There's a reason the human eye, after millennia of evolution, remains one of the most sophisticated instruments for observing the cosmos, especially when it comes to spotting the unexpected. While modern telescopes and sensors excel at capturing vast amounts of data, they often struggle with the very nuances that the human brain is wired to detect. Take something as fleeting as an aurora's delicate ripples or a meteor shower's faintest streaks. Algorithms, programmed to prioritize clarity and consistency, might dismiss these as noise or glitches. But to an observer like Maria Mitchell, America's first professional female astronomer, these subtle disturbances told a story. Night after night, she documented atmospheric distortions on Jupiter and Venus, shimmering irregularities that machines would later classify as technical errors. Yet her notes revealed real phenomena, like the way Venus's atmosphere bent light in ways cameras couldn't fully capture. What gave these skywatchers such an edge? Part of it lies in our biology. Unlike a camera lens fixated on a single point, the human eye thrives on motion and contrast. Peripheral vision, for instance, acts like an early warning system, catching sudden flashes or movements at the edges of our sight, like a comet's unexpected appearance or the flicker of a dying star. This instinctive sensitivity to change meant that 19th-century observers often spotted celestial events purely by accident, simply because their brains were tuned to notice anomalies. When Edward Emerson Barnard discovered Jupiter's moon Amalthea in 1892, it wasn't through a calculated search. He was studying the planet's storms when his peripheral vision caught a faint dot where none should be, a discovery that would have been easy to miss in today's automated sky surveys. But here's the fascinating twist. Modern astronomy is starting to recognize the value of this human-machine partnership. Projects like the Hubble Space Telescope's archival reviews now combine AI with crowdsourced analysis, asking volunteers to flag anomalies that algorithms might overlook. It's a nod to the past, where the intuition of observers like Mitchell and Barnard filled gaps that technology couldn't. The future might lie in hybrid systems, where AI handles the brute force data crunching while human eyes, trained by centuries of skywatching, spot the irregularities that machines dismiss. After all, the universe doesn't always reveal its secrets in tidy, predictable ways. Sometimes you need a biological brain to catch what a silicon one might ignore. Let's talk about the kind of math that could bend the cosmos to its will. No screens, no silicon, just ink-stained fingers and a stubborn belief that the universe could be understood on paper. In the 1800s, calculating a comet's path wasn't a job for computers. It was a marathon of human intellect. Astronomers like Johann Franz Encke would spend months scribbling equations, factoring in every gravitational tug from planets they couldn't even see, just to predict when a comet might swing by Earth. And here's the astonishing part, they often got it right within days. Encke's namesake comet, for example, was tracked so precisely that its 1822 return was predicted to the hour, a feat that would still impress today. How did they do it? Newtonian mechanics became their compass. Every orbit was a puzzle of forces, with each planet's gravity tweaking the path like invisible hands nudging a rolling ball. The math was grueling. Imagine solving 1,000-variable equation by hand, but the results were uncanny. Urbain Le Verrier took this to the extreme when he noticed Uranus wobbling in its orbit as if something massive were tugging at it. No telescope had spotted the culprit, but Le Verrier's calculations pointed to a hidden world, Neptune. When astronomers finally aimed their lenses where his numbers said to look, there it was, a planet discovered not by chance but by pure mathematics. Now contrast that with today's approach. Modern orbit predictions rely on software that crunches data at lightning speed, but there's a catch. These programs often assume the solar system's major players are already accounted for. Tiny discrepancies, the kind a 19th-century mathematician might chase down as clues, get smoothed over as rounding errors. That's why some researchers argue we've grown complacent. When the hypothetical planet 9 was proposed in the 21st century, its existence was inferred from oddities in distant objects' orbits, the same kind of anomalies Le Verrier would have pounced on. Yet instead of notebooks filled with differential equations, we wait for supercomputers to simulate possibilities. Could blending old and new methods crack the case? Projects like the Dark Energy Survey are now revisiting manual observation techniques, pairing them with modern tech to scan the skies for Planet 9's faint signature. It's a reminder that sometimes the sharpest tool for decoding the cosmos isn't a faster processor, it's a human mind willing to wrestle with the numbers until they confess their secrets. After all, the next celestial breakthrough might not be hiding in a dataset, but in the margins of a 200-year-old calculation, waiting for someone to connect the dots. Some of the most intriguing mysteries in astronomy aren't found in the depths of space, they're hidden in the yellowed pages of old observatory logs. Take Epsilon Aurigae, a star that puzzled astronomers for over a century. In the 1840s, observers noted its light dimming dramatically every 27 years, as if something vast were passing in front of it. But without photography or spectrographs, the cause remained a guess. Fast forward to 2008, when modern astronomers revisiting those handwritten records realized the star's dimming matched the orbit of a hidden companion, a dusty disk so faint today's telescopes had overlooked it. Those 19th century notes held the key all along. This isn't an isolated case. Dig through enough archives and you'll find stars that simply vanished. One observer in 1885 sketched a brilliant pinpoint in the constellation Cygnus, a star so bright it outshone its neighbors. By the time telescopes powerful enough to study it were built, the star was gone. No explosion, no remnant, just silence. Modern surveys focused on capturing vast swaths of sky might miss such fleeting events, but a human eye, fixed on one patch of heaven's night after night, couldn't ignore it. Now, teams are racing to digitize these fragile records before they crumble. Projects like the Digital Access to a Sky Century at Harvard are scanning glass photographic plates and notebooks, uncovering anomalies that algorithms skip. One researcher recently stumbled on a 19th century sketch of a star flaring violently, a possible precursor to a supernova we've never recorded. Could these forgotten observations hold clues to rare cosmic events? Preserving this data isn't just about nostalgia, it's a scientific goldmine. When astronomers combined antique eclipse records with modern satellite data, they found subtle changes in the sun's rotation, evidence of solar cycles stretching back centuries. Imagine what else might surface as more archives come online. The next great cosmic revelation might not come from a new telescope, but from a researcher scrolling through a digitized logbook, connecting dots across time. After all, the universe keeps its secrets where we least expect them, sometimes in plain sight, waiting for the right moment to be seen again. For centuries, the moon was thought to be a silent, unchanging world, until patient observers in the 1800s began noticing something strange. Flickers of light, unexplained glows, shadows that seemed to shift where no shadow should be. John Herschel, son of the famed astronomer William Herschel, meticulously recorded these oddities during his lunar observations, describing sudden bright spots near the crater Aristarchus that appeared and vanished within minutes. Other astronomers like Wilhelm Beer and Johann Heinrich Mädler mapped similar anomalies, transient patches of mist or flashes that defied explanation. At the time, theories ranged from volcanic activity to reflections off hypothetical lunar ice. But what if these long-dismissed accounts hold clues to one of the moon's biggest mysteries? Modern telescopes, for all their power, have a blind spot when it comes to these fleeting events. Automated surveys scan vast areas of the sky, but they're optimized for consistency, often filtering out brief, unpredictable changes as noise. When a team in 2012 tried to verify historical reports of lunar flashes using high-speed cameras, they caught a handful of events, likely meteor impacts, but missed the subtler glows Herschel described. Even NASA, a lunar reconnaissance orbiter with its eagle-eyed cameras, struggles to spot these phenomena in real time. The irony: those 19th century observers, with their modest telescopes and unflagging patience, might have been better equipped to document them. So what were they seeing? One compelling theory points to gas. Recent probes have detected traces of radon and helium seeping from the moon's crust, hinting at sporadic underground releases. When sunlight hits these escaping gases, they could briefly glow exactly the kind of ephemeral radiance Herschel noted. Another possibility: electrostatic dust. The moon's surface, bombarded by solar wind, can send charged particles skimming overhead, creating faint, shimmering veils. But the most tantalizing idea involves the moon's wispy, transient atmosphere, a tenuous layer of gases that forms and dissipates unpredictably. If those old sketches of lunar mists were real, they might have captured this elusive exosphere in action. Amateur astronomers are now picking up where the pioneers left off. Groups like the Association of Lunar and Planetary Observers collaborate with professionals, using backyard telescopes to monitor the moon for flashes and glows. Some even cross-reference their findings with Herschel's original notes, searching for patterns. In 2020, an amateur in Japan recorded a vivid flash near the crater Plateau, a spot flagged as active in 1836. Coincidence? Maybe not. As modern tools and historic data converge, we might finally solve a puzzle that's lingered for 2 centuries. The next breakthrough in lunar science could come from someone staring through an eyepiece, just as Herschel did, waiting for the moon to reveal its secrets one fleeting glimpse at a time. Solar storms don't announce themselves with fireworks, they creep up slowly, leaving subtle clues in the sun's mottled face. That's what Richard Carrington learned in 1859, hunched over his telescope as he sketched the sun's blemishes day after day. His meticulous diaries, filled with sunspot counts and intricate drawings, didn't just document the weather on our star. They predicted a storm so fierce it set telegraph wires ablaze and painted the skies crimson as far south as Cuba. Today, we call it the Carrington event, but back then, it was just another entry in his notebook, a quiet warning buried in the rhythm of ink and paper. What made Carrington's observations so extraordinary wasn't just the storm he caught, it was the patterns he uncovered. Modern satellites like NAS, a solar dynamics observatory, capture the sun in dazzling high definition, tracking every flare and coronal mass ejection in real time. But they've only been watching for a few decades. Carrington's records, along with those of his contemporaries, span centuries, revealing cycles too slow for short-term tools to grasp. Sunspots ebb and flow in 11-year rhythms, but deeper beneath the surface, there are longer, subtler pulses, trends that only emerge when you stitch together generations of handwritten notes. Take the Maunder minimum, a 70-year lull in solar activity during the 1600s. Without historical sunspot diaries, we might have dismissed it as a data gap. But those records proved the sun could go eerily quiet, with profound effects on Earth's climate. Fast forward to today, and researchers are combing through similar archives to understand why modern solar cycles seem weaker than those in Carrington's era. Could we be slipping into another minimum? Satellites can't tell us, but a notebook from 1880 might. The real power of these old records lies in their imperfections. Unlike sterile digital data, sunspot diaries are rich with context. Marginal notes about cloudy weather or a shaky telescope mount help scientists filter out noise, turning quirks into clues. When Carrington sketched the sunspot group that sparked his famous storm, he included something most sensors would ignore: its odd shape, like 2 sprawling ink blots. That detail later helped physicists link sunspot geometry to flare potential, a connection modern AI might miss without human context. Now, teams are racing to digitize these fragile pages before they crumble, feeding centuries of analog wisdom into predictive models. One project even uses Carrington's methods to train neural networks, teaching them to spot long-term patterns the way he did. The goal: to foresee the next Carrington event before it blindsides our power grids and satellites. Because while today's tech watches the sun in snapshots, those old diaries remind us the star we orbit plays a long game, and its secrets hide in the patience of those who dare to look. Charles Messier spent 18 years sweeping the skies with nothing but a 4-inch telescope, determined to catalog every fuzzy patch that might distract him from his real quarry, comets. Night after night, he charted nebulae and star clusters, not because they interested him, but because they didn't move. His famous Messier catalog, now a treasure trove for astronomers, began as a list of false alarms. Yet in that relentless process of elimination, he discovered 13 comets, each one a testament to the power of human persistence. Fast forward to today, where automated surveys like Pan-STARRS scan the entire sky each night with billion-pixel cameras, flagging thousands of potential comets, yet some still slip through. The difference lies in how we look. Messier and his contemporaries didn't just hunt comets, they knew them. They memorized star fields, noticing when a single speck of light didn't belong. That intimate familiarity meant they could spot a comet's faint glow, even as it emerged from the cosmic background, something algorithms struggle with. Take Comet Neowise in 2020. Discovered by a space telescope just 4 months before it became visible to the naked eye, it had already been swinging toward us for millennia. Had an observer like Messier been scanning that patch of sky a year earlier, they might have caught its approach when it was still a whisper in the dark. Modern surveys have their own blind spots, software designed to filter out asteroids, those unchanging dots marching predictably across the sky, sometimes dismisses comets in their early stages, when their tails are still forming. That's where amateurs are stepping in, reviving old-school techniques. Groups like the International Comet Watch train volunteers to review telescope images manually, looking for the subtle haze of a comet's coma that algorithms might reject. In 2019, an amateur in Crimea spotted Comet Borisov, the first known interstellar visitor after Oumuamua, using nothing but a backyard telescope and patience. The irony: some of today's most exciting comet discoveries happen when technology and tradition collide. The Lincoln Near-Earth Asteroid Research Project, for instance, uses AI to flag potential comets, but it was a human operator who noticed one candidate's peculiar motion, leading to the discovery of Comet NEAT. Perhaps the future of comet hunting isn't about choosing between old and new methods, but combining them, letting machines handle the tireless scanning while human eyes, trained by centuries of sky watching, decide what's worth a closer look. After all, comets don't follow scripts, and neither do the best discoveries. In the winter of 1883, astronomer Edward Emerson Barnard peered through his telescope at a patch of sky near Orion and saw something that shouldn't exist: a faint, starless smudge drifting silently against the backdrop of stars. No tail, no coma, just a shadowy streak moving with purpose. At the time, he dismissed it as a flaw in his lens or a trick of the atmosphere. But what if Barnard had stumbled upon one of the solar system's most elusive phantoms, a dark comet? These hypothetical objects, chunks of rock and primordial ice stripped bare by eons of solar wind, reflect almost no light, making them nearly invisible to conventional telescopes. Yet 19th-century observers like Barnard might have recorded them without realizing it. Their journals are peppered with references to empty nebulae that moved like comets but lacked the characteristic glow. Some even sketched strange, tailless streaks crossing their fields of view, only to vanish when other astronomers tried to confirm them. For over a century, these accounts were filed away as curiosities until modern astrophysicists began puzzling over gaps in our solar system's debris population. Where were all the burned-out comets, the skeletons of icy bodies that had lost their volatile coatings? The answer might lie in those old observations. Infrared telescopes like NAS and Neowise have recently detected a handful of ultra-dark objects skirting the inner solar system bodies, so dim they're only visible when they pass in front of bright stars or emit faint heat signatures. Their orbits match the erratic paths of traditional comets, but their surfaces resemble asteroids. Could these be the same shadowy wanderers Barnard and his peers glimpsed? One tantalizing clue comes from an 1892 report by William Minor Fleming, who documented a void near the Pleiades that seemed to swallow starlight as it passed. Modern simulations suggest such an effect could occur if a dark comet's dusty envelope briefly blocked background stars, a phenomenon our ancestors witnessed but couldn't explain. Now, researchers are racing to match historical anomalies with new infrared data. A team at the University of Hawaii recently cross-referenced century-old star charts with neowise detections and found 3 cases where phantom nebulae aligned with the predicted paths of dark comets. One, spotted in 1878 near Ursa Major, traced an orbit now linked to a known ultra-dark object called 2020 OG. The implications are staggering. If these objects have been hiding in plain sight for centuries, our solar system's inventory of debris might need a rewrite. This isn't just about solving an old mystery, it's about rethinking how we classify celestial nomads. The line between asteroids and comets has always been blurry, but dark comets could represent an entirely new category, cosmic chameleons that defy easy labels. As we comb through more historical records, we might uncover other overlooked phenomena, objects dismissed as optical illusions that were actually pioneers of an unseen population. The next time a telescope catches a flicker where nothing should be, perhaps we'll remember Barnard's ghostly smudge and ask, are we finally seeing what the 19th century couldn't name? Venus has a secret one that's been flickering at the edges of human vision for over 300 years. It's called the Ashen light, a faint, ghostly glow on the planet's night side where no sunlight should reach. Francesco Bianchini first documented it in 1721, sketching pale, shimmering patches on Venus's shadowed face. Others followed. Sir William Herschel described it as a phosphorescent gleam, while 19th century astronomers like Edward Maunder compared it to Earth's auroras. Yet modern probes armed with hyperspectral cameras and ultraviolet sensors struggle to confirm it. So what were these observers seeing? A trick of the eye or something stranger happening in Venus's toxic skies? Theories abound. Some argue it's an optical illusion, the human brain filling in gaps when staring at a bright crescent against the black of space. But that doesn't explain why seasoned astronomers like Bianchini, who meticulously tracked Venus for decades, reported the glow only intermittently, often when the planet was at specific orbital positions. Others propose atmospheric luminescence, chemical reactions in Venus's clouds, similar to Earth's airglow, where molecules release energy as light. Recent data from Japan's Akatsuki orbiter hints at ultraviolet emissions in the planet's upper atmosphere, but nothing visible to the naked eye. Then there's the volcanic angle. Venus is a world reborn, its surface scarred by thousands of volcanoes. If even a few are still active, their eruptions could pump sulfur compounds high into the atmosphere, where sunlight might trigger eerie afterglows. Infrared scans from the European Space Agency's Venus Express did spot transient hot spots, possible lava flows, but no direct link to the Ashen light. More provocative are theories involving electrical phenomena. Venus's thick clouds crackle with static, and some researchers speculate that planet-wide lightning or electrostatic discharges could create brief, diffuse illumination. It's a tantalizing idea, but without a smoking gun, the mystery endures. Now, scientists are turning history into a roadmap. By cross-referencing historical reports with modern orbital data, they've identified potential windows when the glow might reappear, specific alignments of Venus's orbit and Earth's vantage point. Private initiatives like the Planetary Society's Light Catch project are recruiting amateur astronomers to monitor Venus with high-sensitivity cameras, hoping to catch the Ashen light in action. Meanwhile, NASA's upcoming Da Vinci mission, which will drop a probe through Venus's atmosphere, could finally settle the debate if it catches a glimpse of the night side's faint radiance. What makes this centuries-old enigma so compelling isn't just the chance to solve it, it's the reminder that some cosmic puzzles demand both cutting-edge tools and the patience of those early skywatchers. Their handwritten notes, once dismissed as quirks of perception, might yet guide us to discoveries hiding in plain sight. After all, Venus hasn't changed. Maybe we're just learning how to see it properly. Mercury has always been the solar system's shyest planet, a fleeting dot near the sun, its surface scorched and its secrets hidden behind a veil of glare. Yet in the 1800s, skilled observers like Giovanni Schiaparelli and John Herschel reported something peculiar. Mercury wasn't just a bare rock. Through their telescopes, they glimpsed faint hazes clinging to its edges, distortions in its silhouette during transits that hinted at something more. At the time, the idea of Mercury having an atmosphere was laughable. How could a world so small and so close to the sun hold onto even a whisper of gas? But those patient skywatchers, sketching its passages across the solar disk with painstaking precision, were onto something modern probes would later confirm. Mercury does have an atmosphere, vanishingly thin and constantly replenished but real. What's remarkable is how they detected it. During transits, when Mercury crosses the sun's face, 19th century astronomers noticed its crisp black disk sometimes appeared fuzzy at the edges, as if blurred by an ethereal veil. Others recorded fleeting glows or color shifts along its limb, subtle enough to dismiss as optical illusions but consistent enough to note in their journals. Fast forward to 1974, when Mariner 10 became the first spacecraft to visit Mercury and detected a wispy exosphere, a barely there layer of sodium, oxygen, and helium, stripped away by solar winds but continually replenished by meteorite impacts and surface evaporation. Those old observations hadn't been flaws, they'd been glimpses of a phenomenon too delicate for modern flybys to prioritize. Here's the irony: today's missions like BP Colombo zip past Mercury at kilometers per second, collecting terabytes of data but often missing the slow, subtle changes those early astronomers documented. Their transit observations, sometimes spanning hours, captured nuances that brief flybys might overlook: the way Mercury's tenuous atmosphere thickens and thins with its day-night cycle, or how solar storms sculpt its tail of escaping particles. This isn't just about Mercury, it's a lesson for studying exoplanets. When we observe distant worlds transiting their stars, we're essentially using the same method Schiaparelli did, watching for faint distortions in starlight that betray the presence of an atmosphere. Those 19th century techniques, patient, detail-oriented, and attuned to anomalies, could revolutionize how we interpret the flickers of alien suns. The real takeaway: in an era of snapshot science where data comes faster than we can process it, there's still immense value in the long game. Mercury's atmosphere didn't reveal itself in a single flyby, but through centuries of accumulated observation, each entry in a weathered logbook adding another piece to the puzzle. As we train our telescopes on exoplanets light years away, we might do well to remember the power of persistence, to sit with the data, as those skywatchers did, until the universe whispers its secrets. Percival Lowell's Mars was a world crisscrossed with precision, a network of straight, dark lines he called canals, stretching across the rust-colored plains like the veins of some colossal machine. From his observatory in Flagstaff, Arizona, he mapped hundreds of them between 1894 and 1916, convinced they were the work of an advanced civilization struggling to survive on a drying planet. His sketches, rendered in meticulous detail, captivated the public and divided scientists. Some hailed him as a visionary, others dismissed the canals as pure fantasy, artifacts of a weary eye straining at the limits of telescopic resolution. But what if the truth lies somewhere in between? Lowell's observations weren't entirely baseless. Modern missions reveal that Mars does have linear features, vast rift valleys like Valles Marineris, and fracture systems etched by tectonic forces. Viewed through the shaky, dust-filtered lens of 19th century telescopes, these jagged geological scars could easily blur into the illusion of straight lines. Atmospheric turbulence plays tricks too. On nights when Earth's air was unsteady, Lowell might have glimpsed fleeting moments where cracks in the terrain appeared artificially aligned, like the mirage of a distant highway shimmering in heat. Even the planet's notorious dust storms, which shift surface patterns seasonally, could have made transient features seem deliberate. The real lesson here isn't just about optics, it's about how expectation shapes observation. Lowell arrived at Mars already believing in a habitable world, and his mind connected the dots accordingly. Yet his mistake inadvertently spotlighted real phenomena. The fractures he misread as canals are now key targets for rovers like Perseverance, which studies them for clues about Mars's watery past. Those cracks might have once channeled groundwater, making them hotspots in the search for ancient microbial life. In a twist of irony, Lowell's discredited maps could guide modern science to its greatest discovery. Perhaps the canal's greatest legacy is the humility they demand. Every era's instruments have blind spots, and every generation's theories carry assumptions. Today, we smirk at Lowell's Martian engineers, but our own interpretations of exoplanet atmospheres or dark matter might one day seem just as quaint. The difference is we have his example to remind us. Sometimes the wrong idea points to the right truth. As Perseverance drills into the rocks of Jezero crater, it's worth remembering that the answers we seek might have been sketched in ink over a century ago, waiting for the tools and the open minds to understand them. Jupiter's stripes aren't just for show, they're massive storm systems, churning bands of gas that stretch across the planet like painted brushstrokes. But sometimes, without warning, entire belts vanish. In 1883, astronomer Andrew Comet trained his telescope on Jupiter and saw something unsettling. The planet's iconic south equatorial belt, normally a bold, dark ribbon, had faded to a ghostly whisper. Other observers soon confirmed it. The belt wasn't gone, but it had dimmed so dramatically that smaller telescopes couldn't detect it. Over the next year, their notebooks tracked its gradual return, a slow resurgence no one could explain. Fast forward to 2010, when amateur astronomers sounded the alarm. The same belt had disappeared again. This time, Hubble's sharp eyes caught the aftermath, a colossal upheaval in Jupiter's atmosphere, where ammonia clouds boiled up from below, cloaking the darker layers beneath in a reflective haze. What's fascinating isn't just that these events happen, but how much we've learned by comparing modern observations with those 19th century notes. Automated systems today might have dismissed the 1883 fading as a sensor glitch, averaging it out over time. But human observers, meticulously sketching Jupiter's face night after night, recorded the exact timing and progression, details that later helped scientists link the phenomenon to planetary-scale climate shift. Those old records revealed something else. Jupiter's belts don't just fade randomly. There's a rhythm, a cycle of collapse and rebirth tied to the planet's deep circulation patterns. When researchers analyzed the timing of historical vanishings, they found clusters every 40 to 50 years, hinting at atmospheric waves or slow-moving plumes we're only now beginning to model. The real surprise came when astronomers dug even deeper into the archives. Galileo's sketches from 1610 show Jupiter with fewer belts than we see today, while 18th century accounts describe transient streaks that no longer exist. These aren't inconsistencies, they're clues. Jupiter's atmosphere is a living, evolving system, and its long-term behavior can't be understood with just decades of data. That's why projects like the Planetary Virtual Observatory and Laboratory are digitizing centuries of hand-drawn observations, turning ink smudges and faded star charts into searchable datasets. When the South Tropical Disturbance, a sprawling storm complex, erupted in 2020, researchers cross-referenced it with a similar event logged in 1870. uncovering patterns no single generation of astronomers could have spotted. This isn't just about Jupiter. Every planet in our solar system has its own cadence of change, cycles too slow for any one mission or lifetime to grasp. Saturn's storms, Neptune's shifting dark spots, even the subtle color variations in Uranus's haze, they all require the kind of long-view science that only blends old and new. The next time Jupiter's belts flicker, we won't just be watching a weather event. We'll be deciphering a language written in gas and time, one that began with a lonely observer squinting through a brass tube, wondering where the stripes had gone. Saturn's rings have always mesmerized us, glittering bands of ice and dust suspended in perfect harmony. But in the 1800s, a handful of sharp-eyed astronomers noticed something strange. Etched across those pristine rings were ghostly streaks, like spokes on a wheel, radiating outward from the planet's shadow. William Lassell, observing in 1848, sketched them as faint, transient lines cutting through the ring's structure. Others, like Johann Galle and Etienne Trouvelot, recorded similar features, their drawings capturing delicate filaments that defied explanation. At the time, many dismissed them as optical illusions, tricks of the eye, or flaws in their telescopes. After all, how could something so ephemeral, so seemingly impossible, exist in Saturn's orderly rings? The mystery deepened when Voyager 1 flew past Saturn in 1980 and captured the spokes in stunning detail. There they were, stretching tens of thousands of kilometers across the rings, appearing and vanishing with no clear pattern. Scientists realized these weren't flaws in old telescopes. They were real, dynamic phenomena, and they hinted at forces at work in the rings that no one had anticipated. The spokes turned out to be clouds of tiny, electrostatically charged particles, lifting briefly above the ring plane before settling back down. But what caused them? The leading theory points to Saturn's magnetic field, which may interact with solar radiation to create temporary levitation. Yet even now, decades after their confirmation, the spokes refuse to follow a predictable schedule, appearing and disappearing like cosmic clockwork with missing gears. What's remarkable is how those early sketches, once doubted, became crucial to understanding these elusive features. When the Cassini mission arrived at Saturn in 2004, scientists pored over historical records, comparing the spoke patterns observed in the 19th century with modern data. They found clues in the timing. Spokes seemed more frequent when Saturn's tilt exposed the rings to more sunlight, suggesting a link to seasonal changes. Without those meticulous old drawings, researchers might have overlooked this cyclical behavior, dismissing the spokes as random quirks rather than pieces of a larger puzzle. The lesson here goes beyond Saturn. Those early observers could have ignored the spokes, chalking them up to tired eyes or faulty equipment. Instead, they documented what they saw, leaving a trail of breadcrumbs for future scientists. Today, as we study exoplanet rings or distant galaxies, we're reminded that the universe is full of fleeting, unexplained phenomena, features that might seem like anomalies today but could be breakthroughs tomorrow. The next time a telescope catches a flicker or a blur in the data, it's worth asking, are we seeing the next great mystery, waiting for its moment to be understood? Uranus doesn't spin like the other planets. It rolls, tipped over at a jaw, dropping 98 degrees. It orbits the Sun like a barrel tumbling sideways, its poles alternately basking in decades of sunlight or plunged into icy darkness. When William Herschel first discovered Uranus in 1781, he couldn't have known how bizarre its orientation was. But by the mid-19th century, as astronomers refined their measurements, the planet's extreme tilt became impossible to ignore. Observers like Johann Gottfried Galle and Urbain Le Verrier scratched their heads, wondering what cosmic violence could have knocked a world so thoroughly off kilter. Their best guess, a collision something massive, ancient, and catastrophic enough to send Uranus spinning sideways. At the time, the idea was radical. The prevailing view of the solar system was orderly, with planets forming neatly from swirling disks of gas and dust. A colossal impact violent enough to tip an entire planet seemed like science fiction. Yet these astronomers, armed with nothing but basic telescopes and celestial mechanics, pieced together clues from Uranus's odd behavior. Its moons, for instance, orbit in the same tilted plane, as if frozen in the aftermath of some primordial shove. Even its magnetic field is off-center, a lopsided signature that modern probes like Voyager 2 later confirmed. The more they studied Uranus, the more it seemed like a scarred survivor of some distant celestial battle. Fast forward to today, and that once controversial theory is textbook science. Supercomputer simulations now show how a young Uranus could have been struck by an Earth-sized protoplanet, a glancing blow that sent it reeling. The impact wouldn't just explain the tilt, it might also account for the planet's mysterious lack of internal heat. Unlike other gas giants, Uranus radiates almost no excess energy, as if the collision blasted away its primordial warmth. But here's the twist. While we've upgraded from hand-cranked calculations to digital models, the core idea remains unchanged. Those 19th-century speculators working with far cruder tools were essentially right. What's even more fascinating is how Uranus's story reflects a broader truth about planetary formation. We now know our solar system's infancy was a demolition derby, with protoplanets jostling for space. Earth's moon likely formed from a similar cataclysm when a Mars-sized body slammed into our planet. Exoplanet studies reveal tilted worlds orbiting distant stars, suggesting Uranus isn't an outlier but part of a cosmic pattern. The real genius of those early astronomers wasn't just their intuition, it was their willingness to question the tidy narratives of their time. Uranus reminds us that some of science's biggest leaps begin as heresies. Long before we had the tech to simulate planetary collisions, the groundwork was laid by observers who dared to imagine chaos in the heavens. As we peer at exoplanet systems with their own wonky orbits, we're following in their footsteps, asking what violent histories might lurk behind the calm face of the night sky. Neptune's deep blue face might look serene from afar, but up close, it's a tempest of chaos. And some of its fiercest storms were first spotted by astronomers peering through telescopes no better than modern backyard models. When William Lassell trained his handmade reflector on Neptune in 1846, just weeks after its discovery, he noted something peculiar, fleeting dark smudges on its disk, shifting position over weeks. At the time, most dismissed these as optical tricks. After all, Neptune was a dim, distant blur, barely distinguishable from a star. But Lassell's sketches, crude as they were, hinted at a truth that wouldn't be confirmed for another century and a half. Neptune isn't just windy. It's home to hurricanes the size of Earth, churning in its frigid atmosphere with terrifying power. When Voyager 2 raced past Neptune in 1989, it vindicated those early observers in spectacular fashion. The probe's cameras revealed the Great Dark Spot, a monstrous storm system as wide as our planet, spinning counterclockwise like a demonic hurricane. Even more astonishing, it had company, smaller dark vortices and methane clouds racing at over 1,000 miles per hour. Yet what's often overlooked is how closely these modern discoveries mirrored Lassell's sketches. His recorded smudges aligned eerily with the latitudes where Voyager later spotted storms, suggesting he'd glimpsed transient eddies in Neptune's violent weather. The real marvel isn't that he saw them, it's that he saw them at all. Modern telescopes, for all their power, face a paradoxical challenge: they're often too precise. Automated surveys prioritize crisp, high-resolution images, but Neptune's faint, slow-moving storms can blur into the noise unless someone specifically looks for them. That's where legacy data becomes gold. When researchers at the University of California sifted through 19th-century logs, they found recurring references to Neptune's blemishes, observations once written off as flawed, now recognized as critical snapshots of the planet's storm cycles. Without those notes, we might have missed a crucial pattern. Neptune's dark spots emerge and vanish every 4 to 6 years, a rhythm linked to seasonal shifts in sunlight across its tilted axis. This isn't just about storms, it's about how science stumbles toward the truth. Lassell wasn't hunting for hurricanes, he was simply documenting what he saw, even when it defied expectations. Today, that spirit of open-ended curiosity guides missions like the James Webb Space Telescope, which revisits Neptune's weather with infrared eyes. But it also underscores a humbling lesson. Sometimes, the tools we need to crack a cosmic mystery aren't just better lenses or faster computers. They're old notebooks filled with the careful scribbles of observers who trusted their eyes enough to record the inexplicable. As we push deeper into the outer solar system, those faded pages might still hold the next great clue. The night of November 12, 1833, wasn't just a meteor shower, it was a celestial avalanche. Across North America, thousands of people scrambled from their beds as the sky erupted in silent fire, streaks of light pouring down like embers from a cosmic bonfire. The Leonid meteor storm, as it came to be known, wasn't just a spectacle. It was a Rosetta Stone for understanding how our solar system evolves. Observers like Denison Olmsted, who counted over 200,000 meteors in a single night, didn't just document the event, they mapped its radiant point, the spot in the sky where the meteors seemed to originate. That simple act of tracing paths backward revealed something groundbreaking. These shooting stars weren't random debris, but fragments of a comet following a predictable orbit. Fast forward to today, and those handwritten logs are rewriting our understanding of cosmic traffic. Modern radar systems like the Canadian Meteor Orbit radar track thousands of meteors nightly, but they've only been watching for decades. The Leonid records from the 1800s, by contrast, span multiple orbits of Comet Tempel-Tuttle, the icy parent of the storm. When researchers compared those antique observations with contemporary data, they noticed something unsettling. The comet's path had shifted slightly, nudged by Jupiter's gravity over centuries. Those delicate orbital tweaks explain why the once epic Leonid storms of the past have softened into gentler showers today, and why they might roar back in the 21st century as the comet's path continues to evolve. But here's the catch. We'd never have spotted this slow-motion dance without those 19th-century notes. Modern sensors excel at spotting debris in real time, but they lack the long view needed to see patterns unfolding across lifetimes. Take the Andromedes, another once mighty shower that lit up skies in the 1840s. By the 1900s, it had nearly vanished, victim of another gravitational shove from Jupiter. Yet buried in old European observatory logs are clues that the shower's debris stream might be reforming, its particles slowly clustering back into a new path. Without those records, we'd have no way to anticipate its potential return. This isn't just about predicting pretty light shows. Meteor orbits are cosmic breadcrumbs, tracing how planets rearrange the solar system's small bodies over millennia. When the Geminid meteor stream, now one of our richest annual showers, first appeared in the 1860s, it baffled astronomers. Unlike most showers which stem from comets, the Geminids were linked to an asteroid, Phaethon. Those early observations became critical when modern probes revealed Phaethon's bizarre behavior. It brightens like a comet near the sun, shedding dust. The mystery, those 1800s records suggest the Geminids were far weaker then, meaning Phaethon's activity has surged, a clue that asteroids might evolve in ways we're only beginning to grasp. So what else might we be missing? With most meteor studies focused on recent decades, we're effectively reading a single page of a multi-volume history. Projects like the NASA Meteoroid Environment Office are now scouring archives, pairing century-old sketches with satellite data to reconstruct lost debris streams. Some suspect the long-defunct Cetids or the enigmatic Eta Lyrids showers that flared in the past but now seem dormant could still hold remnants of ancient comets, their orbits warped beyond recognition. Others wonder if undiscovered streams lurk in the blind spots between radar stations. The real lesson here isn't just about meteors. It's a reminder that the cosmos doesn't keep time on human scales. Those patient skywatchers, scratching quill to paper under flickering lamplight, were chronicling changes too slow for any one lifetime to see. Their legacy isn't just in the data they left. It's in the quiet understanding that some celestial stories take centuries to tell. Eclipses have always been more than just celestial spectacles. They're nature's ultimate experiments, offering rare glimpses into the sun's hidden mechanics. When Captain James Cook set sail for Tahiti in 1769 to observe the transit of Venus, he unknowingly laid the groundwork for a new era of eclipse science. But it was the total solar eclipses of the 19th century that truly transformed our understanding of the cosmos. Teams of astronomers, lugging bulky equipment to remote corners of the globe, meticulously sketched the sun's corona, the wispy, ethereal halo visible only during totality. Their drawings, often dismissed as artistic flourishes, later revealed structures in the corona that modern satellites now track as predictors of solar storms. One of the most tantalizing phenomena they documented, shadow bands, those elusive, shimmering ribbons of light that dance across the ground moments before totality. Early observers like Samuel Williams during the 1780 eclipse described them as undulating waves of shadow. But without photography, the phenomenon remained a mystery. Today, we know these bands are caused by Earth's turbulent atmosphere, refracting the last slivers of sunlight. Yet amateur eclipse chasers still replicate those early methods, unfurling white sheets or using smartphone cameras to capture their fleeting patterns. It's a testament to how much we can learn from techniques pioneered with nothing more than paper, pencil, and patience. The eclipse of 1878 stands out as a turning point. As astronomers fanned out across the American West, one team in Wyoming made a critical observation. The positions of stars near the sun's edge appeared subtly shifted. At the time, it was chalked up to atmospheric distortion, but decades later, Einstein's theory of general relativity would explain it. The sun's gravity was bending starlight, warping space itself. Those handwritten notes, buried in observatory archives, became crucial evidence when scientists revisited the data after Einstein's predictions. The same expedition also recorded detailed coronal streamers, structures we now associate with the sun's magnetic field, proof that eclipses serve as time capsules, preserving data whose significance might only emerge generations later. Modern eclipse science still leans on these historical anchors. When the 2017 Great American Eclipse crossed the U.S., researchers compared contemporary corona images with sketches from 1878, tracing how the sun's magnetic activity has evolved over cycles. Citizen scientists armed with DSLR and filters recreated the shadow band studies of their 19th century predecessors, proving that some mysteries still demand human eyes. Even now, as satellites like Parker Solar Probe plunge into the sun's atmosphere, eclipse observations remain irreplaceable. their ground-level perspective capturing nuances that space-borne instruments might miss. What makes these events so powerful isn't just the science they enable, but the continuity they represent. Every time the moon's shadow sweeps across Earth, it connects us to the observers of the past, those who stood under the same darkened sky, scribbling notes by lantern light, trusting that someday someone would decipher their clues. As we prepare for the next total eclipse, we're not just chasing shadows. We're stepping into a legacy of curiosity, one that stretches back to Cook's voyages and beyond, reminding us that the best cosmic laboratories aren't always built. Sometimes they're borrowed from the heavens themselves. Variable stars were the universe's first timekeepers long before atomic clocks or pulsars. These flickering beacons taught us that the heavens aren't static. Take Mera, the wonderful star, whose dramatic brightness swings were first recorded by David Fabricius in 1596. Watching it fade from view over months, only to flare back to visibility, shattered the ancient belief in an unchanging cosmos. Then there's Algol, the demon star, whose eerie dimming every 2 days and 20 hours felt like clockwork to John Goodricke in 1782. Born deaf, Goodricke relied on his extraordinary visual acuity, meticulously tracking Algol's dips and correctly guessing they were caused by a dimmer companion star eclipsing its brighter twin, a theory we now know as the first documented eclipsing binary. His notebooks, filled with candlelit observations, are a masterclass in how limitation can sharpen insight. What's astonishing isn't just that these observers caught these patterns, it's how modern astronomy risks losing them. Automated sky surveys like the Zwicky Transient facility scan millions of stars nightly, but their algorithms often prioritize dramatic, one-off events over slow, rhythmic changes. Mera's 400-day pulsation cycle, too gradual to flag as interesting next to a supernova. Algol's precise eclipses, dismissed as routine when stacked against gamma-ray bursts. Yet buried in those overlooked rhythms are clues to stellar evolution. Mera's pulsations, for instance, reveal how aging stars shed mass before becoming planetary nebulae, while Algol's dance showcases how binary systems exchange material over millennia. That's where historical records become irreplaceable. When researchers at Harvard digitized antique variable star catalogs, some handwritten in Cyrillic or Latin, they uncovered cycles spanning centuries that no modern telescope could replicate. One 18th-century log from Prague showed Mera's period has shortened by a day every millennium, a subtle shift hinting at changes in its internal nuclear furnace. Another, from a Jesuit observatory in China, confirmed Algol's orbit is slowly tightening as the stars spiral toward each other. These aren't just curiosities, they're time-lapse films of stellar lives, painstakingly recorded by observers who didn't live to see the payoff. Now, a grassroots movement is bringing this tradition into the digital age. Projects like the American Association of Variable Star Observers train amateurs to monitor these stars using backyard telescopes, blending their data with centuries-old archives. In 2021, a retired teacher in New Mexico noticed an unusual flare in a usually steady variable, a tip-off that led professionals to spot a previously unknown companion star. Others are revisiting lost variables from 19th-century catalogs, stars once deemed too faint or erratic to study, but now detectable with modern sensors. It's a reminder that the cosmos still whispers its secrets to those willing to watch and wait. The real magic of these cosmic clocks isn't just in their ticking. It's in the way they connect us across generations, linking Goodricke's ink-stained notebooks to today's pixelated sky maps. Every time a star like Mera swells and fades, it's not just sharing its own story, it's echoing the patience of those who first taught us to listen. The zodiacal light is one of the night sky's most haunting spectacles, a faint, pyramid-shaped glow rising from the horizon just before dawn or after dusk, so delicate it's often mistaken for the first hint of sunrise. 19th century observers like E. Barnard described it with awe, comparing its luminosity to the Milky Way's softest strands, but today, even seasoned astronomers struggle to spot it. The culprit, light pollution, the same artificial glow that drowns out stars, has all but erased this cosmic whisper from our skies. What makes this loss so poignant is how much those early records reveal. Detailed logs from desert expeditions and mountain observatories show the zodiacal light was once vivid enough to cast faint shadows, a detail modern observers can scarcely believe. At the time, theories about its origin ranged from the poetic to the prescient. Some imagined it as sunlight reflecting off the wings of celestial angels, while others, like astronomer Giovanni Cassini, correctly guessed it was caused by dust, countless microscopic particles scattered along the plane of the solar system. But here's where those antique observations get fascinating. Modern probes like NASA's Juno mission have detected streams of interstellar dust grains, likely debris from passing comets or even remnants of the primordial cloud that birthed our planets. The zodiacal light isn't just a pretty glow. It's a fossil record of the solar system's construction, and those 19th century sketches captured its structure with surprising accuracy. Their drawings often noted asymmetries in the light's shape, subtle bulges now linked to dense bands of debris left by comet trails or asteroid collisions. Yet the real mystery lies in what we've lost. Urban sprawl and skyglow have dimmed the zodiacal light to near invisibility for most of humanity, cutting us off from a phenomenon that guided navigators and inspired myths for millennia. Dark sky advocates point to places like Chile's Atacama Desert or Namibia's Namib, where the light still shimmers as it did for Barnard. These pockets of preserved darkness aren't just nostalgic, they're scientific time machines. By studying the zodiacal light under pristine conditions, researchers have spotted fluctuations that hint at real-time dust influx from passing comets, something satellite data alone might miss. Efforts to combat light pollution are yielding unexpected dividends. Communities that adopt shielded streetlights and warmer LED tones report not just clearer views of the zodiacal light, but also healthier ecosystems, fewer disoriented migratory birds, more active pollinators. It's a reminder that protecting our view of the cosmos isn't just about astronomy. It's about rebalancing our relationship with the night itself. When the next generation gazes upward, perhaps they'll see what those 19th century skywatchers did, not just a ghostly glow, but a bridge to the solar system's hidden past, written in dust and light. Auroras aren't just dazzling light shows, they're cosmic telegrams carrying urgent bulletins from the sun. Long before satellites could monitor solar storms, 19th century scientists like Elias Loomis turned these shimmering curtains into data, stitching together global auroral reports to trace invisible forces connecting Earth and its star. When the sky erupted in crimson on September 2, 1859, observers from Havana to Rome scrambled to document the spectacle. Loomis, then a professor at Yale, collected hundreds of eyewitness accounts, mapping the aurora's reach with meticulous precision. His conclusion: the phenomenon wasn't random. It followed patterns, flaring most intensely along curved lines that hinted at Earth's hidden magnetic architecture. Those hand-drawn maps, inked on yellowing parchment, became the first blueprints of what we now call the magnetos, a revelation that space wasn't empty, but threaded with invisible forces. The storm behind that aurora, now known as the Carrington event, was so powerful it electrified telegraph lines, shocking operators and setting paper ablaze. In Scotland, operators disconnected their batteries and found messages still pulsing through the wires, powered solely by celestial currents. But what makes these records invaluable today isn't just their drama, it's their precision. Carrington's own sketches of the sunspot that triggered the storm show a sprawling cluster with a distinctive shape, a detail modern researchers use to correlate historical solar activity with ice core samples. Those correlations revealed something startling. Carrington-level storms aren't once-in-a-millennium flukes. They recur every century or so, with weaker but still dangerous strikes peppering the gaps. This is where history becomes a survival guide. When engineers design satellites or power grids today, they lean on 19th-century extremes as stress tests. The Quebec blackout of 1989, which left millions without power for hours, was caused by a solar storm half the strength of Carrington's. That near-miss spurred modern shielding standards like Faraday cages for transformers and radiation, hardened electronics in orbit. But there's a catch. Our infrastructure has grown exponentially more vulnerable since the telegraph era. A Carrington-level storm today could collapse global navigation systems, knock out communications, and trigger cascading blackouts lasting months. That's why scientists are racing to decode past solar cycles. By combing through antique oral logs and comparing them with tree-ring carbon isotopes, they've reconstructed a timeline of solar tantrums stretching back millennia. The pattern: the sun has a temper, with cluster storms erupting during periods of heightened activity, like the one we're entering now. Teams at NASA and the National Oceanic and Atmospheric Administration use these historical benchmarks to calibrate early warning systems, knowing that the next Carrington could arrive with far less fanfare than its predecessor. The real lesson of those oral records isn't just about preparing for disaster, it's about humility. Loomis and his contemporaries didn't have the tools to understand why the sky burned in 1859, but they trusted their observations enough to preserve them. Today, as satellites monitor the sun's every hiccup, we're reminded that the most critical data might not come from our newest instruments, but from the careful notes of those who watched the heavens with wonder and a pencil. The next time the auroras dance, they won't just be putting on a show, they'll be passing down a warning written in light across generations. The Great Comet of 1811 didn't just streak across the sky, it seeped into the fabric of human culture, leaving its mark on everything from fine art to battlefield strategies. For an astonishing 17 months, this celestial visitor hung in the heavens, its sprawling tail stretching like a brushstroke across the cosmos. Unlike today's comets, which often vanish from view within weeks, this one became a constant companion, its presence so enduring that vintners in Europe credited it for that year's unusually warm autumns, dubbing the resulting wines Comet vintages, some of the most celebrated vintages of the century. Artists like John Linnell immortalized its sweeping arcs in vivid paintings, while poets wove it into verses as a symbol of divine portent, but the comet's influence reached far beyond aesthetics. Military historians have long puzzled over the timing of Napoleon's invasion of Russia in 1812, a campaign that began just as the comet reached peak brilliance. Some scholars argue its ominous glow stirred superstitious unease among troops, while others suggest its appearance may have indirectly delayed supply lines as farmers across Europe paused to interpret its meaning. Whether cosmic coincidence or catalyst, the comet's shadow loomed over one of history's most pivotal conflicts. Scientifically, this comet was a game-changer. Astronomers like Jean-Louis Pons tracked its path with unprecedented precision, using its prolonged visibility to refine calculations of orbital mechanics. Their painstaking observations revealed how comets could loop around the sun in elongated paths, a revelation that helped dismantle the ancient belief that these were atmospheric phenomena. The comet's multi-year journey also offered the first clear evidence of how solar heat could vaporize icy nuclei, creating those spectacular tails, a process now fundamental to our understanding of cometary behavior. What makes the Great Comet truly remarkable, though, is how it bridged worlds. In an era before artificial light pollution, its brilliance united scientists, artists, and everyday stargazers in shared wonder. Today, as most comets dart past unnoticed by the public, its legacy reminds us that cosmic events once held collective power, a reminder cultural astronomers are reviving by linking modern discoveries to human stories. The next time a comet graces our skies, perhaps we'll see it not just as a scientific curiosity, but as a thread connecting us to centuries of skywatchers who found meaning in the stars. Maria Mitchell's discovery of a comet in 1847 wasn't just a scientific breakthrough, it was a quiet revolution. Working from her rooftop observatory on Nantucket, she spotted a blurry streak others had overlooked, earning her a gold medal from the King of Denmark and becoming America's first professional female astronomer. But her true legacy wasn't in that single moment of recognition. It was in the decades of meticulous observations that followed. Night after night, she charted star clusters and solar prominences, her notebooks brimming with details too nuanced for the telescopes of her time. When Vassar College hired her as their first astronomy professor, she didn't just teach, she built a program that trained generations of women to see the universe with the same rigor and wonder. Then there's Annie Jump Cannon, whose fingers danced across glass photographic plates at Harvard, sorting stars by their spectral lines long before computers could attempt the task. While male colleagues theorized about cosmic distances, Cannon and her fellow computers, underpaid, overworked women classified hundreds of thousands of stars by hand, creating the Harvard classification system that's still the backbone of stellar astronomy today. Her genius lay in recognizing patterns invisible to machines, the subtle shifts in hydrogen lines that revealed a star's temperature, or the way calcium signatures hinted at age. Early computers programmed to replicate her work failed spectacularly, lumping stars into crude categories her eye had deftly separated. The universe, it seemed, resisted simplification, and Cannon's intuition grasped what algorithms couldn't. Yet for all their contributions, these women fought erasure at every turn. Mitchell's comet was initially credited to her patron, a male benefactor who'd lent her the telescope. Cannon's system was published under her boss's name, her labor buried in footnotes. Their stories expose a painful truth. Science rarely remembers those it doesn't deem worthy of attention. Even now, when we picture an astronomer, the image that comes to mind is more likely to be Galileo or Hubble than Mitchell bending over her brass telescope or Cannon squinting at a plate under lamplight. Rediscovering their work isn't just about justice, it's about reclaiming lost knowledge. When modern researchers revisited Cannon's notebooks, they found anomalies she'd flagged but never had the resources to investigate. Stars with peculiar spectra that we now recognize as white dwarfs or pre-planetary nebulae. Mitchell's solar observations, once dismissed as amateurish, proved crucial for understanding how sunspots influence Earth's magnetic field. These weren't just overlooked details, they were missed opportunities, clues that could have accelerated discoveries by decades if given proper attention. The lesson here goes beyond astronomy. When we exclude perspectives, whether by gender, race, or circumstance, we don't just lose voices, we lose entire ways of seeing. Cannon's classification succeeded because she noticed what others filtered out. Mitchell's cometary orbits were precise because she accounted for variables theorists ignored. Science thrives not in uniformity, but in the friction of diverse minds wrestling with the same sky. As we push deeper into the cosmos, perhaps the greatest tool we have isn't a bigger telescope, but a wider lens, one that lets us finally see the full tapestry of those who have mapped the stars. Long before GPS satellites circled the globe, sailors navigated the open ocean by something far more ancient: the steady rhythm of the stars. Nathaniel Bowditch, a self-taught mathematician turned naval astronomer, spent years hunched over sextants and chronometers, tracking the precise moments when stars crossed the meridian. These star transits were more than navigational aids. They were cosmic metronomes, ticking with a regularity that even the finest mechanical clocks couldn't match. His logs, filled with timings accurate to the second, didn't just guide ships, they revealed something startling about Earth itself. The planet wasn't a perfect timekeeper. It wobbled ever so slightly on its axis, like a spinning top losing speed. Bowditch's meticulous records, compared across decades, helped quantify that wobble, proving that even the heavens weren't as fixed as they seemed. What's astonishing is how closely those handwritten tables align with modern atomic clocks. Today's cesium oscillators measure time to within a billionth of a second, yet when researchers cross-checked Bowditch's 18th-century star transit data against atomic timestamps, the margins of error were negligible. His methods, relying on nothing more than a telescope and a steady hand, captured celestial movements with near-perfect precision. This wasn't just luck, it was a testament to the power of disciplined observation. Naval astronomers like Bowditch understood that stars didn't just mark positions, they anchored time itself, offering a universal constant in an era when local clocks often disagreed by hours. But their work did more than sync chronometers. Those star logs became the scaffolding for global timekeeping systems. When railroads and telegraphs demanded standardized time zones in the 19th century, it was Bowditch's celestial reference points that provided the blueprint. Even now, when atomic clocks need calibration, astronomers still refer to quasars, distant star-like objects whose positions were first mapped using the same transit techniques perfected by sailors centuries ago. The wobble Bowditch detected, known as precession, still factors into satellite launches and deep space navigation, proving that some corrections are timeless. This raises a deeper question: how much of our modern world rests on foundations laid by star watchers? From the GPS in your phone to the timing of stock market trades, systems we take for granted trace back to celestial observations. When radio telescopes measure pulsar rotations, or when archaeologists date ancient eclipses using Babylonian clay tablets, they're continuing a tradition that began with navigators squinting through brass telescopes. The stars, it turns out, don't just guide us across oceans, they thread through the very fabric of human progress, stitching together past and present in ways we're only beginning to appreciate. Perhaps the real lesson lies in the humility of those early astronomers. They didn't just collect data, they listened to the cosmos, trusting it to reveal patterns no single lifetime could encompass. In an age of instant digital updates, there's something profoundly grounding about recognizing that some truths unfold across centuries, and that the next great discovery might be hiding in the margins of a 200-year-old logbook, waiting for the right moment to be seen. In the mid-19th century, a simple prism cracked open the universe's deepest secrets. When Gustav Kirchhoff trained his spectroscope on sunlight, he wasn't just analyzing rainbows, he was reading the chemical fingerprints of creation itself. Those colored bands, once dismissed as optical curiosities, became a Rosetta Stone for decoding cosmic composition. Kirchhoff's breakthrough came when he matched dark lines in the solar spectrum, later named Fraunhofer lines, to the bright emission lines of heated elements in his lab. Sodium, iron, calcium, they were all there, stamped across sunlight like celestial barcodes. For the first time, humanity could prove that the same elements burning in Earth's laboratories also fueled distant stars. This wasn't just chemistry in space, it was a revolution in perspective. Astronomers had assumed stars were fundamentally different from our humble solar system. But Kirchhoff and his collaborator Robert Bunsen shattered that notion, revealing a universe built from familiar ingredients. Their patient, methodical approach comparing lab flames to starlight line by line stands in stark contrast to today's automated sky surveys. Modern telescopes like the Sloan Digital Sky Survey capture millions of spectra nightly, feeding them into algorithms that classify stars in seconds. Yet those early handwritten spectral atlases, with their painstaking annotations, still hold surprises. When researchers recently revisited Kirchhoff's original notebooks, they spotted faint absorption lines that modern instruments often overlook, hints of rare elements or subtle atmospheric effects that standardized software filters out as noise. The legacy of these spectral pioneers extends far beyond stellar chemistry. Their foundational work now guides the hunt for alien worlds. When the James Webb Space Telescope analyzes exoplanet atmospheres, it's using the same principle Kirchhoff established. Every molecule absorbs light at unique wavelengths. The telltale dip of methane or water vapor in a distant world's spectrum could betray the presence of life, a possibility those 19th century scientists glimpsed but couldn't yet prove. Even the search for technosignatures, evidence of advanced civilizations, relies on spectral anomalies, like artificial gases that shouldn't exist in nature. What's most remarkable is how these old techniques are finding new life. Teams studying galactic archaeology, the history of our Milky Way, now combine antique spectral plates with AI, uncovering stellar motions too gradual for modern snapshots to reveal. Others are applying Kirchhoff's methods to interstellar dust, decoding its composition by how it dims and reddens starlight. As we peer deeper into cosmic dawn with telescopes like JWST, we're essentially using 19th century tools to answer 21st century questions. How did the first stars form? What molecules seeded the building blocks of life? The answers may lie not in flashy new instruments alone, but in the careful, curiosity-driven observation that turned sunlight into a story. The next great discovery might not come from a bigger telescope, but from someone revisiting those faded spectral plates, asking what Kirchhoff might have missed. Imagine a telescope that doesn't just peer across space but across time. That's the power hidden in century-old glass plates and handwritten logs, where generations of astronomers left behind more than just data. They left a roadmap of the sky's slow dance. Projects like Harvard's Digital Access to a Sky Century aren't just archiving history, they're unlocking a new kind of time machine. By digitizing over 500,000 photographic plates from 1885 onward, researchers are stitching together a cosmic film strip, frame by painstaking frame. Take the case of Delta Cephei, a pulsating star whose rhythmic brightening and dimming first revealed how to measure galactic distances. Modern telescopes can track it in real time, but those antique plates, they capture its behavior across world wars, solar cycles, and technological revolutions, context no snapshot can replicate. What makes these records indispensable isn't just their age, it's their imperfection. Unlike today's pristine digital images, early photographs are riddled with quirks, chemical streaks, dust motes, even fingerprints. But those flaws act like timestamps, revealing atmospheric conditions or lens distortions that modern software can now filter out to extract unprecedented precision. When a team reprocessed 1890's plates of the Pleiades star cluster, they discovered subtle shifts in stellar positions, evidence of gravitational tugs from unseen brown dwarfs that contemporary surveys had missed. It's as if the past is whispering corrections to the present. The real game changer, though, is how artificial intelligence breathes new life into these analog treasures. Handwritten observer logs, once indecipherable to algorithms, are now being parsed by neural networks trained to spot anomalies in cursive script. At the Vatican Observatory, a machine learning model sifting through 19th-century solar sketches flagged recurring notations about veiled sunspots, transient blurring once dismissed as poor optics. Cross-referenced with modern solar wind data, those entries aligned perfectly with coronal mass ejections, suggesting historical observers had documented space weather events before the concept existed. This synergy of old and new reaches beyond academia. Amateur astronomers worldwide are reviving longitudinal studies, the art of tracking single celestial objects for decades using apps that collate their observations into crowd-sourced timelines. One volunteer in Australia, logging Jupiter's Great Red Spot since 1980, recently noticed its shrinkage accelerating, a detail that spurred professional studies into the storm's unexpected decay. Meanwhile, the Zooniverse platform enlists thousands to transcribe antique star catalogs, uncovering forgotten variables or vanished nova that algorithms classify as noise. The lesson here isn't nostalgia, it's necessity. In an era of data deluge where telescopes like the Vera Rubin Observatory will generate 20 terabytes nightly, we risk losing the forest for the pixels. Those long-dead skywatchers understood something we're relearning. Some cosmic truths unfold slower than a human lifetime. Their notebooks, etched with corrections and marginalia, remind us that discovery isn't just about resolution or speed, it's about continuity. When the next anomaly lights up the sky, whether it's a flickering quasar or an interstellar visitor, we'll need more than cutting-edge sensors to understand it. We'll need the patience to listen to the past. The night skies of the 19th century weren't just observed, they were lived in. Astronomers like Maria Mitchell and William Herschel didn't merely collect data, they wove themselves into the fabric of the cosmos, tracking celestial movements with a devotion that bordered on reverence. What's astonishing isn't just what they saw with their modest telescope, it's how much they understood without the crutch of modern technology. They didn't have supercomputers to model planetary orbits or satellites to map the sun's tantrums. Instead, they had notebooks, patience, and an unshakable belief that the universe would reveal itself to those who watched long enough. Their legacy isn't confined to yellowed pages in observatory archives. It's etched into the very foundations of modern astronomy. When NASA Parker Solar Probe braves the sun's corona, it follows a path first hinted at by sunspot sketches from the 1800s. When algorithms predict the next great meteor shower, they're building on star charts scribbled by candlelight. These skywatchers didn't just document the heavens, they taught us how to read them, discerning patterns in the chaos that our high-speed tools sometimes miss. Their greatest gift wasn't the data they left behind, but the method they perfected, observing not just with lenses but with time. Yet this treasure trove of knowledge is fragile. Many original observation logs, ink fading, paper crumbling, are one careless touch away from being lost forever. Projects like the Astrophysics Data System and the Library of Congress's digital preservation initiatives are racing to scan and transcribe these documents, but they need public support. Every digitized page is more than a relic. It's a potential key to unsolved cosmic mysteries. A marginal note about a flickering star in 1880 might hold clues about stellar evolution we've yet to grasp. A sketch of Jupiter's storms could refine our climate models for gas giants light years away. So here's the challenge and the invitation. The next time you step outside under a clear night sky, take a moment to look up the way they did. Not just to see, but to witness. Trace the arc of a passing satellite, but also let your eyes linger on the steady glow of a planet or the slow drift of the moon. In that act, you're joining a chain of curiosity stretching back centuries, where every observation, no matter how small, adds another stitch to the tapestry of discovery. The future of astronomy isn't just in bigger telescopes or faster algorithms, it's in remembering that sometimes the universe speaks loudest to those who listen slowly. The stars haven't changed, only our way of seeing them has, and perhaps in bridging the old and the new, we'll find the next great revelation waiting where it's always been, above us, patient and unchanging, ready for anyone willing to look.